Now, in this video presentation, I'll be looking at acceleration of circular motion. Remember that the circular motion, the motion of a body in a circular track. And if the body moves in a circular track, it has an acceleration. And the acceleration is what we want to consider today. And I need to tell you that there are two types of acceleration. We have the radial acceleration, which we also call the centripetal acceleration, and then we have the tangential acceleration. Now, the vector sum of these two accelerations give the net acceleration of a body in circular motion. Okay, so I can start by writing the net acceleration of a body is equal to the sum, the vector sum of its radial acceleration. You can also call that centripetal acceleration, AC, plus vector sum, ET, tangential acceleration. Okay, but this video, I'm going to derive an expression and also explain these two types of acceleration. And we need to know it and know the be able to clearly differentiate between these two types of acceleration. Now, but first of all, we need to understand that the velocity of a body in circular motion, that is in vector notation, is given by the product of its angular velocity, that is the cross product, and radius r. We are going to, in this video, consider r as a vector quantity. That's the radius vector. And then come to see that later. So that if I differentiating this equation with respect to t, I have dv over dt. That gives me my net acceleration, ant, net acceleration. That will equal to, now how do you differentiate a product? I'm sure you must have done product rule before in differentiation. If you have not, you will have to take a look at how to use product rule. Maybe I should quickly write down the product expression. If y is the product of two variables, u and v, or this is u, this is v, and that each of them is a function of x, then what is the y dx? The y dx is giving us, let's see, u first. Keep the variable u constant, then multiply by the derivative of v with respect to what? The x, plus you keep v constant. Next, then multiply by the derivative of the of u with respect to what? To x. Okay, you can see that now. This is the formula we use in differentiating um, products of two expressions or algebraic expressions. We have to differentiate them, you know. So I'm going to just translate this or apply this to differentiate this so that again my dv over dt is equal to, if I want to keep this one constant first, that's my omega cross product multiply by this, the RT, the r over dt, then plus keep r constant next because I'm taking this as my u and this as my v, then by the cross product of that is the omega over dt. Of course, cross products is of course you encounter this in vectors. In vectors, we have the dot product of two vectors, we have the cross product of two vectors. The dot product of two vectors is a scalar quantity, but the cross product of two vectors is a vector quantity, and acceleration is a vector. Okay, by close examination or by close inspection, we clearly see here that this one is leading us to the two types of acceleration. This expression gives us the net acceleration. Let me call that ANT, net, is equal to this acceleration plus this other acceleration. But which one do we call centripetal acceleration, that is radial acceleration? And which one do we call the other one, tangential acceleration? Okay, let me start with this one and then on the extreme right. Now, you can see that, come back here now, the omega over dt is called the angular acceleration. Angular acceleration is angular displacement, rate of change of angular displacement. So that's why we have it there. And it means that if this is this, then r cross angular acceleration will be given by what? That will be equal to the tangential acceleration, at, subscript t. Now, how is this so? Consider a body moving in a circle, center O, for instance. If the body is at this point, now the radius vector is directed away from the center. This is the radius of the circle, r. You can see that the direction of r is away outward, let's say at this point. Now, angular acceleration directed in such a way that it is perpendicular to the point in that circular path. So this is the direction of my angular acceleration. Now, if you have, for instance, in vectors, in dealing with the cross product of two vectors, suppose you have A cross B and the result is C. It means that this vector C is the result of taking the cross product of these two vectors. It's another vector. How is it directed? It is directed at right angles to the plane that contains vector A and B. Okay, this is how to understand it. So vector C is always at right angles to the plane containing these two vectors. Of course, this is the angle between them. You can call that theta. You know? So here now we can see that R is directed this way and alpha, which is my angular acceleration that way. It means that the product of these two, remember the angle between them is this right angle, is going to be a vector that lies along the tangent at A or at this point A, for instance. So that acceleration, that's why it is called tangential acceleration. So it is the product, the cross product of the radius vector and the angular acceleration vector. We call that tangential acceleration. And since the angle between alpha and the radius vector is 90 degrees, of course, you know that if you take the cross product of two vectors, the result is always r times alpha magnitude. This is magnitude sine. Okay, this is a complete expression for the cross product of two vectors. Okay, but since the angle is 90, sine 90 is 1, it means that we are going to have maximum acceleration. Okay, so r cross alpha will be equal to what? R times what? Alpha. That's in terms of magnitude. So that my tangential acceleration in terms of magnitude is the radius magnitude multiplied by the angular acceleration magnitude. That gives me the expression for my angular what? That is tangential what? Acceleration. So it means that if we come back to this equation, this right-hand side, this expression on the right-hand side represents tangential acceleration. It acts in a direction, tangent to that point or to that body along that circle. Okay, so let's see the next expression. Okay, the next expression has omega cross product the r over the t. Okay, now consider again that you have a body moving in a circle like this center O. Let's say at a time t, the body is at point A. Okay, the radius vector is also directed away like this r. Okay, so let's say after some other time t, the body moves to a point B. Okay, radius vector is also directed away. Now you can see that though the radius is constant in magnitude, but the direction of r is not constant. R is constant in magnitude. As long as the circle remains the same, our radius R is constant. You can see very clearly here that the radius vector is changing in terms of direction. So that the change in R, if I call this R2 and I call this R1, that is this R1 represents the direction and magnitude of this radius vector acting at point A, and R2 stands for the radius vector both in magnitude and direction. Then we can see that this line that joins A and B becomes the change. We can call that the displacement. Okay, that's as the body moves from point A to point B. So that velocity of the body V is given as change in displacement over change in time. Okay, now our ds is the same thing as what radius r2 minus r1. Okay, and this r2 minus r1, the same thing as my dr over over what? Over time t, over dt, or what have you. Okay, so you can see that now that this the r over ds, which means my dr over dt, the same thing as my ds over dt. That gives me the v. And this v represents the velocity, the linear velocity of the body at different points. Let's say at point A, the velocity v, is given by this symbol. That's the. Then at point B, of course, you can also have the velocity there. All right, so that's the velocity of the body as it moves around the circle. And sometimes it could be constant, sometimes it could be changing. Okay, now we know that this is omega. Come back here now. I can write this cross product, this one now. I'm going to rewrite it here. So that omega cross r, or the r over dt, is the same thing as omega cross product of v. Because I've shown you that this dr over dt is my v. And the cross product of these two is omega times v sine theta. And since, okay, consider this again, the body in a circle. Now, this is my theta. My radius vector is this r1. This is my r2. Okay, I have this as my displacement. So if the velocity is along the tangent, okay, and the omega, my angular velocity is also given like this, perpendicular, because angular velocity is always acting in a direction radially out of, out of the paper. It's directed away, upward, like this, out of the paper. Okay, so that the product of these two, this is my v, my vector b, this is my omega. So the product of these two will be a vector directed towards the center. That's what we call the radial acceleration or centripetal acceleration. So you can see this shown here. So omega and v, the product is AC, which is my centripetal acceleration, AC. That is a magnitude. So since this is 90, in terms of magnitude, it is omega multiplied by v. Okay, so that is my centripetal acceleration. So that at the end, you can write net acceleration is equal to centripetal acceleration, okay, vector sum plus tangential what? Acceleration. Okay. Now, if I want to represent this so that I can find the magnitude, because this is just in vector form. Okay, let's say I have at this point, the acceleration of the body at this point is that's AC directed this way towards the center, and the other one is directed at along the tangent, that is 80 tangential. Then if you take this right angle, it means that the two accelerations are at right angle. My net acceleration is a vector acting or represented by this arrow. That is my net acceleration, ANT. Okay, so we can place an angle here, theta, to find the angle between them. So that using Pythagoras theorem, my net acceleration squared is equal to this one squared plus tangential acceleration squared. So that my net acceleration will be equal to the square root of AC squared plus AT squared. That is my net acceleration.